Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Tavish. In the last video, we had a comprehensive discussion about property analysis of pure components and the binary systems, and specifically emphasized on the thermodynamic property analysis of these systems. In this video, we will learn how to perform property analysis of the ternary mixtures, specifically for the mixtures that form azeotrops, learn how to perform property estimation of the non-databank components, and how to perform data regression to determine the parameter values from the experimental data. For the ternary analysis, let's consider the following case study. Consider a ternary mixture of ethyl acetate, ethanol and water at 101.325 kilopascal. So you are asked to find all the azeotrops of the mixture using NRTL Haddon or Cornell model. Specify the type of azeotrops and singular points, draw distillation boundaries and residue curve maps for this ternary mixture, and based on the synthesis of ternary map, propose a split of distillation columns for the separation of ethyl acetate. So let's open Aspen Plus and solve this exercise. Open a new case without any default template. Add 3 components, go to the find option and search for ethyl acetate. Put the search criteria equal to ethyl acetate and find now. So here is the component ethyl acetate, add to the selected compounds. Second component is ethanol, add to the component list. And the third component is water, also add to the selected compounds. Close this window. So we have added 3 components. Let's rename the component as E-acetate. Also rename the ethanol as ethanol. Go to the next input window and search for NRTL HOC model. Again go to the next option and review the binary interaction parameters. Still Aspen says that required input information is incomplete. Go to the next option. So Aspen property system wanted us to review the binary interaction parameters, and the status has been changed from the required input incomplete to required properties input complete. Let's run the property analysis. So now the status has been changed from input complete to results available. So at this moment we are able to run the property analysis. To perform the ternary analysis, go to the analysis option. Here we have option of ternary diagram that can be used to generate the ternary map for a ternary mixture and check the azeotrops. Also there is option of residue curves that is used to design the distillation scheme considering total reflux. Aspen has also integrated residue curves in the ternary diagrams. So let's go to the ternary diagram option. The window pop-ups with the 4 different options. First option guides towards the help regarding Aspen distillation synthesis using ternary diagrams. Next option is find azeotrops of the system. Third option is use distillation synthesis ternary maps. And the fourth option is continue to Aspen Plus ternary diagram. Let's open the 3 options side by side and view what is the difference between these 3 options. This is azeotrope search. Let's open continue to Aspen Plus ternary diagram option. And also open the ternary diagram use distillation synthesis ternary maps. So all of these 3 options together guide towards the ternary analysis. Here the azeotrope search only search the azeotropes. You simply need to select the components included in the ternary system. Once the components are selected, you can shift the units to any pressure units, adjust the pressure at which you want to determine the azeotropes. Also there is option to select the appropriate model for the analysis, as well as you can select vapor liquid or vapor liquid liquid system. You can change the units of the temperature as well. Let's consider as default setting. Once the input is complete by selection of the components, you can proceed towards azeotrope search in the output section. Here the pure component information is provided as the component name, normal boiling point temperature, and the classification of the node. You can proceed to the azeotrope. For the given system, there are 4 azeotropes and the corresponding temperature of the azeotrope is also given. The classification regarding whether the node is saddle node or unstable node, whether the azeotrope is homogeneous azeotrope or heterogeneous azeotrope, how many components are there in the azeotrope, and what is the composition of the azeotrope against specified pressure and given azeotrope temperature. If you want, you can shift the composition from mole fractions to the mass fraction as well. Also, you can adjust the units of the temperature as well. Unstable node has the minimum boiling temperature of the azeotrope and that corresponds to the 3 component azeotrope and where the appropriate composition of the 3 components is given. Whereas the other azeotropes with the 2 components are given for the binary systems. You can notice all the singular points including the pure components and the azeotropes in this window. So this search option is only useful for the search of the azeotropes. The other option is regarding the Ternary diagrams. Here you can plot the Ternary diagram using appropriate property method, valid phases for the Ternary diagram, corresponding pressure at which the Ternary diagram needs to be plotted, and also you can specify the number of tie lines in the phase envelope. You can also go to the phase envelope to view the composition of the phase envelope, and also you can view the equilibrium compositions. In the Ternary diagram, the first component appears in the right corner of the triangle, second component appears at the top of the triangle, and the third component appears in the left corner of the triangle. So if you want to specify where the component should appear, you can select the component according to your choice. So once we are okay with the component selection, property methods, phases and the pressure, you can run the analysis. This is the Ternary diagram, where you can notice 3 vertices, one in the right corner, the top corner and the left corner corresponding to the pure components, the binary mixtures on the sides of the triangle and the 3 component mixture inside the triangle. Here is the phase envelope where you can notice liquid-liquid equilibrium, and outside the phase envelope you can notice the vapor phase and the Ternary mixtures. So in the Ternary diagram analysis, you have only very limited options to play with the triangle and its appearance. The third option is the distillation synthesis. Distillation synthesis option is in fact the combination of Ternary diagram and azeotrope search, where you have the features of the azeotrope search at the top of the navigation, and also you can go to the Ternary plot. So let's stick to this distillation synthesis for further discussion and close the windows of azeotrope search and the Ternary diagram. So unlike azeotrope search, you have the option to select the property model for the vapor-liquid equilibrium as well as for the liquid-liquid equilibrium. By default, the bases are the mole fractions. If you want, you can switch to the mass fraction base as well. Further, in the distillation synthesis, you can calculate the residue curves, as there is a separate option of residue curve in the Ternary analysis. Also, you can view the azeotropes of the system, view the distillation boundary, and also view VLL envelope in the diagram. There is also an option to select the isovolatility curve. If required, you can check this option as well. So once this setting is okay, you can proceed to the output of the distillation synthesis analysis. Here there is option of the pure component. Again, this is very similar to the azeotrope search option. You can view the azeotropes and all the singular points on the Ternary diagram. In the same window, you can proceed to the Ternary plot. You can notice that now the plot input window is active instead of the Explorer tab. Before further discussion, let's first delete the Ternary diagram from the analysis section. Reinitialize the calculations to get rid of the error from the status bar and run the simulation once again. You can get very valuable information from this Ternary diagram regarding the nature and behavior of the Ternary system. Left side of this window represents different settings of the Ternary diagram. You can change the pressure at which you want to calculate the Ternary system. You can view or hide the information presented on the Ternary diagram, including information of the azeotropes, distillation boundaries, residue curves, tie lines, boiling point temperatures. Also, the plate temperature is mentioned, at which 2 immiscible liquid phases becomes unseparable. At the center, you can view right angle triangle of the Ternary diagram. The vertex of this Ternary diagram indicates pure components along with their boiling temperatures. The sides of the Ternary diagram represents binary mixtures. The binary azeotropes are also mentioned on the sides of the triangle. For instance, heterogeneous binary mixture of water and ethyl acetate forms at 71.39 degrees Celsius with composition of approximately 67% ethyl acetate and 33% water. Similarly, the azeotrope of ethanol and ethyl acetate as well as azeotrope of ethanol and water are mentioned on the sides. The ternary azeotrope is given at 70.33 degrees Celsius. The blue region in the diagram indicates the phase envelope where two immiscible liquids are in equilibrium with each other as connected by the tie lines. The green lines represents the distillation boundaries that clearly separates the ternary diagram into three different regions. One region lies over here, the other region over here, and the third region over here. For still distillation, it is not possible to cross the distillation boundary from one region to another region. Besides, you can use different diagram editing tools on the right side of this window. At the top, there is an option to add the tie lines in the phase envelope. Then there is an option to add the residue curve, either a random residue curve or a residue curve with a specific ternary mixture composition. Then you can add a marker at any point inside the ternary diagram. You can draw a free line inside the triangle. You can switch between right angle triangle and equilateral triangle. Also, you can rotate the axis to any desired position. And there is an option to view the grid line inside the ternary diagram. The grid line facilitates reading of the ternary mixture composition, where vertical line represents the composition of ethyl acetate in the ternary mixture, horizontal lines indicates the composition of ethanol, and the diagonal lines represents the composition of water. In fact, 1 minus the value corresponding to the y-axis or x-axis crossing the diagonal line is the composition of water. For instance, let's take a marker and place somewhere over here. So you can read the composition of ethanol from the horizontal axis as 0.55, the composition of ethyl acetate from the vertical grid line as around 0.15, and the composition of water from the diagonal line. So 1 minus 0.7 is the composition of water in the ternary mixture. You can also view the boiling temperature of this ternary mixture by right click and add boiling temperature. So at the given composition, the boiling temperature of the mixture is 73.24 degrees Celsius. Similarly, you can read the composition from the equilateral triangle, where the left bottom corner indicates pure water, right bottom corner indicates ethyl acetate, and the top corner indicates pure ethanol. To read the composition of water, just follow the diagonal lines those are parallel to the binary mixtures of ethanol and ethyl acetate. For instance, at this point, follow the grid lines that are sliding downward to the right side and read the composition from the binary mixture of water and ethanol. For the given marker, the composition of water is around 0.3. Similarly, you can read the composition of ethyl acetate in the ternary mixture. Just follow the grid lines. Those are parallel to the binary mixture of water and ethanol. Those are sliding downward to the left side, and read the composition from the bottom axis. For the given point, the composition of ethyl acetate is around 0.15. Likewise, the composition of ethanol in the ternary mixture. Just follow the grid lines. Those are horizontal and parallel to the binary mixture of water and ethyl acetate. The composition of the marker can be read for the ethanol at the binary mixture of ethanol and ethyl acetate, that is 0.55 at this moment. You can change the settings for the presentation of the ternary diagram. For that purpose, just right click and go to the properties. Here you can change the settings of the label font and the font size and the position of the toolbar. In the curves tab, you can change the color and the styles of the lines. I personally prefer to use a different color for the residue curves and also slightly a thicker line for the residue curve. You can change the lines, either the tie lines or any user defined line, or you can change the settings of the envelope. I prefer to use slightly a lighter color for the phase envelope. You can change the settings of the markers. Let's make the marker size a slightly bigger one for the azeotropes as well as user defined markers. And similarly, you can change couple of other settings. Once you are okay with the settings of the ternary diagram, you can click OK. So now the tie lines are more clearly visible in the phase envelope. Those were previously hidden because of the darker blue color of the phase envelope. You can add as many as residue curves in the ternary diagram as you prefer. So simply click where you want to add the residue curve. It will automatically pick the composition and add the residue curve there. Arrow lines in the residue curves guides toward higher boiling temperature composition that can be obtained in the still distillation process. Or in other words, the point towards the head of the arrow indicates the reboiler composition and the tail of the arrow indicates the composition in the condenser. In the exercise, you are asked to find all the azeotropes of the mixtures, specify the types of the azeotropes and singular points, draw distillation boundaries and residue curve maps of this ternary diagram that we have done so far. Another question was to propose a split distillation column for the separation of ethyl acetate based on the synthesis of the ternary map. The ternary map is a very helpful tool to develop a scheme of the distillation columns to purify any of the components from the ternary mixture. So you are asked to develop a distillation scheme to produce a pure ethyl acetate. For that purpose, let's consider a ternary mixture given by the same marker. You can define it as a feed stream. Let's label it. For that purpose, right click and add the text. You can add feed as the label to this marker. So now you have the feed stream with around 14.7% ethyl acetate, 55.7% ethanol and around 29.6% water. For the sake of convenience, let's pass a residue curve from this marker. So first, let's consider what is permissible and what is not permissible while designing the distillation scheme from the ternary mixtures. The first point is, while designing a distillation column, any separation is permissible that passes the same residue curve from two different points. Let's pass a line that crosses the same residue curve from two different points. For instance, this line. So distillation is permissible for the given ternary mixture for which the composition in the reboiler will correspond to the ternary composition at this point. Let's add a marker from this point, whereas the composition of the distillate will correspond to this point. Add a marker over here as well. So the given feed will split into the reboiler composition and the distillate composition. Another constraint is you cannot pass the distillation boundary while using the distillation column for the separation. So it is not possible to shift the composition from this region to the region with the higher concentration of ethyl acetate. One possibility is to change the pressure that shifts distillation boundary and the azeotrope. The other possibility is add extra amount of water to this distillate product and bring the composition somewhere in between the phase envelope so that the two different liquid phases can be separated with the liquid-liquid phase separation processes. So let's imagine you have added an extra amount of water to the distillate product and bring the composition of the layer here. Let's add another marker to the new composition that is obtained by adding the water to the distillate product of the first distillation column. Now this product will separate between water phase and ethyl acetate phase, and the compositions of the two phases will lie on the boundary of the phase envelope. The rich ethyl acetate phase will have the composition over here, and the rich water phase will have the composition of the phase envelope on the left side. So these are the two different liquid phases. Those are immiscible in nature and obtained by adding the water to the distillate product of the first column. Let's add another line that connects the liquid-liquid two phases. Now you can follow the residue curve in the second distillation column to produce a pure ethyl acetate. Let's consider this point as a feed for the second distillation column. So any distillation process will be permissible that intersects this residue curve at two different points. Let's pass a line that intersects the residue curve at two different points. For instance, this line. There will be two products, one over here as a pure ethyl acetate, and that will be obtained in the reboiler, and the other product will be somewhere here and will obtained in the distillate. So the distillate will be close to the ternary azeotrope and the reboiler will produce a pure ethyl acetate product. So this is how you can develop a separation scheme for given ternary mixture that forms azeotropes in the nature. Although there can be so many other options to develop a separation scheme, one of them is the pressure swing distillation process, but this is another alternative that can be used to separate a ternary feed into pure ethyl acetate product. You can also represent the process scheme using a process flow diagram where the feed is sent to the first distillation column where nearly a ternary azeotrope is formed as the distillate product, and the other is the reboiler product that is rich in the water composition. So water is mixed with the distillate product to produce two phases that can be separated with the phase separation. One is the water phase and the other one is the ethyl acetate phase. The ethyl acetate phase can be passed through the second distillation column to produce ethyl acetate as the reboiler product, and the remainder from the top distillation column where the water will be added to the nearly ternary azeotrope mixture and two different liquid phases will be obtained that can be further separated. So this process will continue to produce pure ethyl acetate from the ternary mixture of ethyl acetate, ethanol and the water. Another subject of today's discussion was to learn how to estimate the properties of the components. Those are not available in any of the databank included in Aspen Plus. So let's consider following example where you are asked to estimate the properties of a non-databank component, here termed as BCMD-UD, based on the structure formula as shown on the right. In the structure formula, the benzene ring is attached with the N-amide group. In fact, this compound is available in the Aspen Plus databank, but we'll consider it as a non-databank component and define as BCMD-UD and estimate the missing properties of this component using structure formula. So let's go to Aspen Plus and see how to estimate the properties of the non-databank components. Let's start a new simulation without selecting any of the default template. Define the component as BCMD-UD. Also define the structure of this component. Go to the draw structure, take the benzene ring from the fragments and attach amide group to this benzene ring. So the required structure of BCMD is defined. Let's save this structure and name the structure as BCMD-UD. Notice that the extension of this file will be .mol that refers to the molecular structure. Close this window. So now we can estimate the missing properties of this component in two different ways. The first method is following the wizard of user-defined components, as we discussed in one of our earlier videos where user-defined component was added to the component list. The other method is switching to the estimation run mode. So let's first discuss how to estimate the properties of the component using user-defined feature. Go to the next option. Here browse the structure as we defined earlier. It will automatically open a molecule editor. We can browse the defined structure as bcmd-ud.mol and we can close this window. So the status has been changed to structure is available. Go to the next option. Here we have two options to get the properties of this component. The first is evaluation using NIST thermodata engine. If the molecular structure as we defined is also available in the NIST thermodata engine, then we can browse the experimental values of parameters and properties to this simulation. Let's try if the structure is available. Press OK. So the NIST thermodata engine has retrieved all the properties and parameters of this component. Those are experimentally determined and stored in the library of Aspen Plus. You can notice that these properties include eccentric factor, critical properties, different parameters for the estimation of mass density, heat of vaporization, solubility parameters, and so on. You can save these parameters to the navigation pane. So you can notice that all of these properties and parameters are stored under the method section in the parameters tab and under pure component properties and parameters. The scalar properties of the component are available in the TDE-1 where the critical properties, molecular weight, standard volumes are given and temperature dependent property parameters are given in the other tabs. So these are all the values and property parameters determined from the experimental data. The second option in the user-defined wizard was to estimate the properties and parameters using Aspen Physical Property Estimation System. So let's try estimate using Aspen Physical Property Estimation System. So it will estimate the properties of this component from the structural information using appropriate property estimation correlations. So let's finish with the estimation using Aspen Property Estimation System and save the properties for this component. The second way to estimate the properties of this component was to switch to the property estimation run mode. Here you have three options: do not estimate any parameter, estimate all missing parameters, or estimate only the selected parameters that you define in the pure component tab, temperature dependent parameter tab, binary tab, or unifact functional group parameters. You don't have to do anything because the Aspen property estimation does not require the definition of the thermophysical property method. So simply run the simulation. The results of the property estimation are available. To view the results of the estimation, go back to the parameters tab under method section and under pure components. The properties estimated by property estimation system are also stored in this section. For instance, the section PCES that stored all the missing properties that were not available for this component. Since we have already determined most of the properties from the NIST thermodata engine, it only evaluated the properties that were missing and were not available in the thermodata engine. If we would have not evaluated the properties using NIST thermodata engine, then all these properties and parameters would have been evaluated using Aspen Physical Property Estimation System. using the same procedure. So these are two different ways that you can use to estimate the properties and parameters of the component that are not available in any of the selected component data banks. Third subject of today's discussion was to learn how to perform data regression to determine the property parameter values from the experimental data. Let's consider following example for the data regression. You are asked to perform liquid-liquid equilibrium data regression of binary system consisting methanol and normal hexane using unique activity coefficient model. Specifically, you are asked to respond what are the default values of binary interaction parameters of unique model, what are the regressed values of binary interaction parameters of unique model, and compare the liquid-liquid equilibrium data, specifically TXX data obtained from NIST thermodata engine, binary analysis using default interaction parameters, and binary analysis using regressed interaction parameters. So for this exercise, you need to define two components including methanol and normal hexane, define property method as unique, and see the values of binary interaction parameters. Then retrieve the experimental data of liquid-liquid equilibrium of this mixture and perform regression using the same unique model and view what are the binary interaction parameters obtained through regression. Once this is done, then you are asked to compare the liquid-liquid equilibrium data obtained through binary analysis with default interaction parameters and regress parameters with the NIST thermodata engine. So let's switch to Aspen Plus and perform this exercise. Let's start a new simulation without selection any of the default template. Define the components as methanol and normal hexane. Then go to the next input information. Here define the method as unique. Go to the next option. These are the default parameters of binary interactions. As you can see from the method section, under parameters, under binary interaction parameters in the tab UNIQ-1. So these are the binary interaction parameters for the unique model, and specifically they will be used to calculate the activity coefficient using unique model. You can notice different sources from which these parameter values can be obtained. Let's switch back to LLE-LIT. You can also view what does it mean by these parameter values. Go to the help option. So here is the mathematical equation of unique activity coefficient model. The parameter values listed in the table correspond to Aij, Bij, Cij and so on. And these parameter values are used to calculate tau ij factor that ultimately appears in other coefficient values, and finally for the estimation of activity coefficient. You can also view the element number corresponding to the parameter. For instance, the first element 1 is Aij and the second parameter is Bij. You can also notice the lower and upper limits of these parameter values as well as units corresponding to each parameter or element. So the first question was what are the default values of the binary interaction parameters. So the default values of Aij, Aji, Bij and Bji are listed over here. Let's switch to the regression run mode. Here you can notice the data is required before running the regression. You can retrieve the experimental data directly from the NIST thermodata engine, or simply you can add the data over here. Let's click new and enter the data type as the mixture. Since we are looking for the experimental data of the binary mixture of methanol and hexane, shift the two components to the right, define the type of the data that we are looking for. Since we are looking for the TXX plot as the liquid-liquid equilibrium data as a function of different temperatures, so we can select that. Go to the data tab. Here you can retrieve the experimental data through NIST thermodata engine. So click retrieve TDE binary data and it says that there are no experimental data available for the binary system. You can try going back to the setup and look for temperature pressure XX data, and let's try again if the same data is available. So it successfully retrieved a range of liquid-liquid equilibrium data points. You can use any of the dataset that has sufficient number of points available for the two phases composition against different temperatures. Personally, I prefer to use the dataset that has maximum number of data points as well as each temperature corresponds to the composition in the two liquid phases. So you can scroll different data sets and see which of the data set is more appropriate. For given example, we can proceed with the binary liquid-liquid equilibrium data 007. You can notice that this data is obtained between 295 to 307 Kelvin, though at two temperature levels only composition in one of the phase is available, but still there are 6 other data points that correspond to different temperatures, and all those points has the composition in both of the liquid phases. So let's save this data. You can remove the data points that does not have the information of the liquid composition in the two phases. Also, you can plot the TXX diagram and check the temperature levels as well as the coverage of the experimental data. So virtually it covers the full span of the binary liquid-liquid equilibrium compositions between the temperature of 293 to 306 Kelvin. So this is sufficient to run the regression and regress the binary interaction parameters. At the same time, we can go to the regression option and perform the regression. To perform the regression, you first have to have a data set. Let's select the data set that we recently saved as D1. Go to the parameters option. Here you need to define the type of the parameter, either generic parameter or the binary parameter, group parameters, group binary parameters, pair parameters, or the chemistry parameters. So let's stick to the binary parameter. Select the name of the model for which the binary interaction parameters has to be evaluated. You need to define the element number, first component and the second component. Similarly, you can fill other columns for regression of the binary interaction parameters. You can provide information of as many as elements as required in the mathematical expression of the activity coefficient from the Uniquack model. Alternatively, you can go to the method section under binary interaction parameters in the Uniquack model and simply copy the information from this table. Let's stick to only 2 elements and their 2 pairs. You can copy this information, go to the regression option under the parameters tab, and you can paste the information here. It will automatically fetch all the information required to regress the element number 1 and 2, their initial values, lower and upper bounds. If you prefer, you can clear the initial values, lower and upper bounds as well as scale factors, and let the regression perform by itself. So now we are ready to run the regression. To run the regression, go to the run option and click OK. So the regression has successfully performed. As you can see in the status, results are available. You can view the results. For that, go to the result option under regression. Here you can see 4 parameters, 2 elements, their value in the SI unit and the standard deviation. So now we can perform the binary analysis using default interaction parameters, then update the parameters and run the analysis again. So at this moment you can notice the values of the 4 parameters. The first parameter is 0.31 and the second is 4.38. Whereas the default value of these parameters were set to equal to 0. So let's run first the binary analysis with the default interaction parameters. Go to the binary analysis, select TXX analysis, select the key component methanol as the second liquid key component, define the temperature limits between 290 Kelvin and 310 Kelvin, shift the units to Kelvin, also change the pressure to correspond to the experimental pressure in Newton per square meter units. Now we are ready to run the binary analysis. So you can notice that the binary analysis is performed between 290 and 296 Kelvin. At this moment we can merge this chart with the experimental chart. Let's change the scale to match with the experimental data. So you can notice that there is a discrepancy between experimental data and the analyzed TXX plot. Now we can go back to the regression and update the parameters. You can notice that the old values were 00 for the first element. The regressed values are different from the previous values. Same is the case for the element 2 or the parameter number 3 and 4. So click OK and you can confirm whether the values have been updated in the Uniquack binary interaction parameters. Yes, the values have been updated and the source has been changed from LLE-LIT to regressed interaction parameters. At this moment we can run the binary analysis again. So go to the binary analysis and simply run the analysis. How this looks like against the experimental data and the TXX plot obtained by default binary interaction parameters. Here is the experimental data. You can merge the experimental data and the TXX plots. Also shift the axis to map the same y-axis, you can clearly notice that the regressed binary interaction parameters has successfully simulated the TXX diagram of methanol and hexane. Let's rerun the binary analysis using default interaction parameters. For that purpose, change the source to APV140 LLE LIT, where the previous or the default interaction parameters has been retrieved. Go to the analysis, run the binary analysis. For the binary analysis, go to TXX option, change the second liquid key component, define the temperature limits between 290 and 310 Kelvin. Also change the pressure to match the experimental data in the units of Newton per square meter. So run the analysis and merge the plot with the previous values. So shift the y-axis to a single y-axis. So here you can clearly compare that the blue line and the green line represents the TXX plot as obtained by default binary interaction parameters. The markers indicate the experimental data, and the red line and the purple line, they simulate the TXX plot using regressed binary interaction parameters. So this is how you can fine tune the binary interaction parameters using regression option given in the Aspen Plus. You can also try with the different default data sources if any of the other data source provides a reasonable simulation of the TXX plot, and make sure that it is very important to have a reliable parameter value set to perform the analysis or do the process simulations. For further analysis regarding ternary mixtures, I propose following practice problem. Consider a ternary mixture of water, methyl-ethyl ketone and normal octanol at 1 atm pressure. The composition of this mixture can be obtained from the flow rates mentioned. So you are asked to identify and locate all the azeotropes and singular points in the mixture using the UNIFAC model, create distillation boundaries and residue curve maps for this ternary mixture, and utilizing the insights gained from the construction of the ternary maps, devise a separation scheme aimed at achieving more than 90% purity for both water and methyl-ethyl ketone in the recovered streams. Also, I suggest a problem for the data regression. Consider a mixture of methyl-ethyl ketone and 1-hexene at 1 atmospheric pressure. So you are asked what are the default binary interaction parameters. Using the NRTL methods, estimate any missing interaction parameters utilizing the UNIFAC model. This estimation can be done right on the window where binary interaction parameters appear. So you only need to check in a box that appears right above the binary interaction parameters. Then create a TXY plot for the mixture based on NIST thermodata engine data. Identify the azeotropic temperatures as well as the bubble point and dew point temperatures for the equimolar mixture. Then conduct TXY analysis of the mixture using both the ideal method and NRTL method, and compare the obtained TXY plots with the experimental data. Also perform regression analysis on the binary interaction parameters and subsequently reevaluate and compare the TXY diagrams. In the next video, we'll move on to the simulation environment and explore different unit sets and learn how you can define a customized unit set. Also, how to draw and manipulate the flow sheet and start first set of unit operations including mixer and splitters. If you think this lecture series is helpful and valuable, then don't forget to share with your other colleagues and friends.